right, so let's talk about this 116 k-means clustering. So this is going to create that data set with 5 clusters. And you can see it's got 5 clusters. Here's the arrays. And here's the standard deviation, which you see is 2 big ones, 0.4 and 0.3, and then 3 small ones with standard deviation of 0.1. So I say, there we are. If you run that, there you get the 3 tight clusters and the 2 loose clusters on the right. So now we've got some data to work with. Now we're going to fit a k-means model telling it that there are 5 clusters, using a fixed random state of 42 just to make everything predictable, and explicitly feeding in what I think is the default, which is to do it 10 times with different initial conditions to make sure we don't get stuck in an anomalous low value prediction. And almost all this code here is just to make the plots. All the actual work is just right up here. K-means and Y prediction is k-means fit. So the actual work is just here. All the rest of it is just to make a pretty picture. And k-means is very fast because you can see it really does something very simple. And there you get it. 5 centroids placed nicely near the clusters and pretty good cluster boundaries, but not perfect cluster boundaries here because it still is trying to fit clusters that are the same size, and therefore it's a little confused by these points that are far from this centroid. All right. And it tries to make them equally far from that centroid, whereas in fact that's not really the best way to cluster this data. All right. So then it was a score. I added the score to this, minus 211. So that's the score, and you want it to be as high as possible, going closer to 0. So here's the first 3 iterations of the model. We give it a random seed of 5, and I set iteration 1, iteration 2, and iteration 3. These are limited by setting the maximum number of iterations to 1, 2, or 3. Now before we didn't set that, so it had some default value, which I think is something like 50. I'm not really sure what it is. But this is going to, probably not that many are required, but here it's going to show me what happens if you do just 1, 2, and 3 iterations and then plot them. So the actual fitting is just a few lines of code, and then the rest is all just plotting it and printing the final scores of the 3 iterations. Okay, so you put them in randomly, label the instances, optimize them, do it again and again. All right, so here's the first random fit. Here's after 1 iteration of moving them to the center. And here's after 2 iterations moving them to the center, or 1, 2, and 3 if you can call it. By the third one, it's actually gotten pretty good. And you can see minus 600, minus 300, minus 200. So it's getting better and better. And remember, the one that completely finished was 211.6. So after just 3 iterations, it's made it to 212.9. So even after 3 cycles, it's almost done, finding a very good solution. So really, I say, very impressive and fast. All right, now we're going to do it with bad starting values. If we change it from 5 to 2 here, and run it again, then it makes really bad starting guesses, where it puts these 2 over here and only has 2 there, and now it's off on the wrong track, so it's going to center this one in between those 2, and then it's pretty much done. It's going to split this big cluster into 2 and combine this into 1, and now your best fit is 220 instead of 211. So that just shows you how it can go wrong. From a bad start, it can get in a bad area and never find its way back to the good area. Now we're going to make the clusters asymmetric. So this is going to multiply the y coordinate by 10. We've done this in previous projects just to see what happens if the data is not, if the 2 coordinates, x1 and x2, are not equally important. So now you get exactly the same diagram, except this axis is 10 times bigger. So now vertical distances are going to seem to be much larger to the model than horizontal distances. And so if we again do the same fitting here, the same plotting, you're going to see the consequences are disastrous for k-means. Whoa, something didn't work. Oh, I missed the first letter in from. Okay. Now I actually put an F down there. All right, let's see how it looks now. There we are. And see now, since it is unwilling to have any vertical distance, and horizontal distances hardly matter at all, it tries to fit everything with horizontal stripes, because this much error is considered less important than, say, 1/10 of that distance vertically. So it's completely screwed up, as you could understand. So that's another issue. And the fit is disastrous, 240,000 when we were looking for 211 here. So it's ridiculous. All right, so now we'll make another data set that is not good for k-means. This is the classic moon-shaped data set. We've used it before. Let me just make a new, throw away this one and start with a clean one. All right, so this is that moon-shaped data set. All right, with one curve, blue curve, and green curve down there. The data are labeled, but we're going to use k-means and fit them without the labels. So you can fit them, and when you do, you'll find with 8 clusters, it fits like this, and you can get a flag there. Then we're going to do the semi-supervised learning task, which is pretty cool. We talked about it before. So this one here is going to have those 50 images. I think I'll just replace this code with that. So this downloads another database of images. These are the first 50 images. You can see they were sort of sorted, and then they stopped being sorted so much with the first 50 labels. And so if we fit the model to the whole training set, that's this, where we use all the labels and we allow 10,000 iterations of logistic regression, an old model we've used before. What would happen if instead of changing the value from 5 to 2, change it from 5 to 10, it would change everything completely. And see, where do we change max iter equals 4? We didn't. Okay, let me go back and answer some of these questions. Up here, before, we didn't set max iter at all. We let it iterate until it reached a natural stopping point. Now, we just set max iter to a few low values just to see what the first 2 or 3 iterations were. That's what was going on up here with max iter. Yep, you set max iter to a low value just to make it stop without trying to converge. Now, and this random seed is indeed random. So if you change it to any number, like 5 to 6 to 7, that will change everything. It's a random number generator. When you seed it, everything will come after that. It's always predictable. So I just tried different values till I found one that produced the demonstration I like. There's no order at all in what the number of random seed does. The only thing is, if we all use the same random seed, we will all get exactly the same output, and that's why I can have flag values appear. Good. Those are good questions. Anyway, let's take a look at this. So here we have the first 50 images shown with their labels. Now, if I just fit a model with all the images and all the labels, that's what this will do. And then it'll print the score, which is 90.68. So this is about 91% success on the test data, I think. Yeah, on the test data. So you have trained data and testing data. So it's 91% predictive on the test data. So that is probably the best you can possibly do with all the real labels. And now we try fitting to just the first 50 instances instead of fitting to all 17 or 1900 of them. Oh, 1400, yeah, okay, which is what we used because we took some out for a test set. So if I fit just 50 of them, those first 50 shown up there, then now I'm only 75% predictive because I don't have a big enough sample to get a good model. So now I form clusters with k-means, and I form 50 clusters. So on the average, there will be 5 different clusters per digit, although I didn't force it to be that way. It'll be however many clusters it decides are good. It's fit 50 clusters. And here are the representative images of those 50 clusters. These are the images that are closest to the center of each cluster. So those are the types of, and now we have to manually label them, 13607. So I did that here, she 13607, and so on. So by manually labeling the 50 representative images, we can then do a model where you fit just those 50. And since you've chosen images that are not just random 50, but the 50 that are most representative, then you get a better job, 84% success, almost 85%, which makes sense. Now you propagate the labels to all instances, where it will take those 50 clusters and apply that label to every instance in the cluster, and then fit to that. And now you get 89%. Remember, the 90.6 is the training with all the original data. And now we're going to remove the outliers, keeping only the 99% that are closest. So we're going to throw away 1% of the instances, the ones that are farthest from their cluster centers. Because those are presumably the ones most likely to be poorly fit. And now we're up to 90.9% accurate, which is even slightly more accurate than the training on everything. So within the noise, it's very successful. And there's a flag to do here by just breaking the data into 20 clusters instead of 50. So that's what I wanted to show you. What would happen instead of changing the value from 5 to 2, right? We already did that. Okay, good. All right, so anyway, that's the practicing fun with k-means. So I'm going to stop this one.